So last week we were looking at chemical equilibrium, and we linked this with what we were doing the other time, that is rate of reactions. So we realized that some chemical reactions only proceed in one direction. That is only forward reaction. They start and then they go to completion or the end, whilst other chemical reactions can go forward and reverse. So we started looking at those reactions, and we look at the concept of equilibrium. And these points here are very key because in today's lesson we'll be solving problems, we'll be looking at objective questions and theory questions. So sometimes the points highlighted here should be taken note of. So those who were here last week, you can just be going through the points when it gets to the self-assessment or the problems. So chemical equilibrium occurs when a reaction and its reverse reaction proceed at the same rate. That is the forward and then the reverse reactions are occurring at the same rate. That is when we say there is chemical equilibrium. So as a system approaches equilibrium, both the forward and reverse reactions are occurring. And the last point is that at equilibrium, the forward and reverse reactions are proceeding at the same rate. I think it's just stating the same points again. So we gave an example. Here we have a closed system where we are heating water in a pressure cooker. So nothing is allowed to go out, nothing is allowed to enter in. So what happens is that the water in the liquid state is converted to vapor. And at equilibrium, you see that the amount of reactant and product remains constant. Okay. So we use this equation where we have N2O4 being converted to NO2. And we were trying to get a formula or an expression to represent the equilibrium. And the rate of forward reaction, we use Kf, that is K forward, will be N2O4, and then the rate of the reverse reaction will be NO2. So we did a lot of derivations and we arrived at this. So that is actually the rate of formation of NO2 over the rate of formation of N2O4. So we got this generalization, that is when you have an equation of this nature. The equilibrium constant, which we represent as Kc in terms of concentration, can be written as this. That is, you just find the concentration of the the products going forward, concentration of the products, raised to their stoichiometric moles. So we have that there. And over the concentration of the reactant, if you are going forward, but if you are going backwards or the reverse, then this becomes the product. A and B becomes the product. Okay. So generally, we say the equilibrium constant is calculated by finding the rate of formation of the forward reaction over the rate of formation of the reverse reaction. So this point is very, very key and important. You should take note of that. So the equilibrium constant can also be expressed in terms of pressure. That is when we are dealing with gases. Yes. So we use partial pressures. So this is another formula in terms of pressure. Then we try to get the equilibrium relationship between Kc and Kp. That is the equilibrium constant in terms of molarity and then the equilibrium constant in terms of pressure. So we use the ideal gas equation. We try to derive a relationship. We realize that N over V is the same as concentration. So when we rewrite, we arrived at this. This becomes another important formula which we need to keep. Okay. So we also looked at the meaning of Kc and Kp. And here we are today. Today we are going to do much more of problem solving. So our first problem is here. We have a reaction that is A being converted to B. So the forward reaction rate, that is Kf, is 3.0 times 10 to the minus 4 per second. And then the reverse reaction rate is 1.5 times 10 to the minus 2 per second. What is the value of the equilibrium constant Keq? Last week we also talked about the fact that the value of the equilibrium constant and its units varies. The units of the equilibrium constant varies because you'll be having different reactions. But in this case, in this question, for instance, we realize there are no units provided. The reason is that you see these units are the same, so they are going to cancel out. So that's why you don't have a unit here. But at other times, you'll be asked to calculate the equilibrium constant and state its unit. So let's give this question some thought. This is an objective question. So let's try hands on this one. And then you can, I want this to be interactive. The other day we were just testing the answers and we want to hear your voices. So when you are done, you can unmute your mic and then speak up. So these objects, are you going for 1, 2, 3, and 4, or 4? And you have to state the reasons why you choose, or you show working by explaining to us. Yes, are we done? This should take us like 2 minutes. 2 minutes is too much. 1 minute is an objective question. So 1 minute. Okay, let me start calling. Yes, Sarafin. Okay, Perez says he doesn't understand. It's a newcomer. Okay, Perez will be looking at this. Let me summarize the whole concept for you. Let me try and summarize the whole concept for you by going back to the previous slide. So with the calculation aspects, let's begin this way. You need to have a previous knowledge on rates of reactions. If not, then let me ask, Perez, did you... Okay, Sarafin is also new. Okay, so Perez and Sarafin, I hope you already treated rates of reactions in your former schools. Okay, no. So I'll just be a bit, I'll try to summarize, because if we try to go back to rates of reactions, it's going to take the whole period. So does this fall under exothermic? And no, that's not it. We are not talking about exothermic and endothermic reaction here. Okay, so let's continue. I think a question is on board. Who has a laptop? Which of you has a laptop so that you'll be made a host and you'll be admitting people that enter? Anyone? Okay, let's continue. Good. So Phoebe, you've done rates of reaction. That's good. Okay. So with a forward reaction, the rate of, when you say rate of reaction, we are looking at the rate at which reactants are being converted to products. So we write a rate law where K stands for the rate constant, and then the square box you see there stands for concentration. So what they are trying to do here is to derive an expression for the rate law. So for the forward reaction, that is, this N2O4 is being converted to NO2. We are trying to get an equation to express how N2O4 will be changed to NO2. So the simple equation is that Kf will be the concentration of NO2 and N2O4. Then with the reverse reaction, we are looking at how NO2 rather will be converted back to N2O4. So we have Kr, concentration of NO2, then raise to the power 2, because here there are 2 moles of NO2 here. So if here is 3, here will become raised to the power 3. So at equilibrium, we see the rate of forward reaction should be equal to the rate of reverse reaction. So if you go back to our slide, this is the rate of forward reaction, this is the rate of reverse reaction. So we say K of that is equal to that. So when we rewrite this expression, we get this. When you cross multiply, you get back to this equation. So this becomes an expression for the equilibrium constant. So we write it as K equilibrium is K forward over K reverse. So generally, to generalize, if you have any equation, let's say 2 moles of A plus 3 moles of B gives us 4 moles of C plus 5 moles of D. If you are to calculate or write an expression for the equilibrium constant, then that equilibrium constant Kc will be equal to, we just write down what you see at the right side, the concentrations. So they'll give you the concentrations as a number. So raised to the power, here was 4. I was assuming, let's take it here to be 4, here to be 5. So the concentration of C raised to the power 4 times the concentration of D raised to the power 5 over that. That is how you go about it. If you are still not getting it, let's look at the worked examples. You get it as we go along. So this formula is very key. If you have a pen and paper or a book there, you should write it down. Copy down this equation and write this. Write this one as well. So this 1, 2, 3 equations are very important. So if you get this one, we can continue. Seraphine and Phoebe, Seraphine, and Kelvin. Perez, right? Perez. Are you okay? Can we move forward to the next slide? Can we move forward? Okay. Okay. Good. It's good. You're following. So we will be talking about this later. So let's make things simple. So this under physics chemistry 2, when we talk about gases, we remember this. This is the ideal gas equation or the ideal gas law, where P stands for pressure, V stands for volume, and then N stands for moles, amount of substance, R stands for the molar gas constant, and T stands for temperature. So what we are doing here is they are trying to find a relationship between Kc, that is the equilibrium constant in terms of concentration, and then the equilibrium constant in terms of pressure. So we see clearly here that, oh, I know N over V will give me concentration. So we divide both sides of the equation by V, which when we rearrange, we get P equals N over V RT. So finally, we'll be getting Kp to be equal to Kc to bracket RT, always to the power delta N. Delta N there stands for the change in number of moles of the product minus the number of moles of the reactant. So you'll be given Kp and maybe you'll be asked to find Kc, or you'll be given Kc, you'll be asked to find Kp. R and T will be given to you, and then delta N you calculate from the equilibrium equation. So back to this question. Those who were here last week, we are waiting for your answers, then we'll explain to those of us who are not here, those who are new here, so that they can follow. So let me call those who are here. Let's see. I think Lisa was here. Lisa, if I call you, unmute your microphone and talk to me. Lisa, are you done with this question?
Yes, please.
What did you get?
0.02.
Okay. So what concepts did you use to arrive at your answer?
The Kc is equal to Kf over Kr.
Very good.
The
so
rate
that
reaction over the rate of reverse reaction.
Okay, that is the rate of forward reaction over the rate of the reverse reaction. Excellent. So you just input the values there, and then you arrive at 0.02. That's good. To explain the point, I asked you to copy down. Okay, sorry, copy down some equations that are very key. You see this is what Lisa used. This equation, that the equilibrium constant, this EQ stands for whether we are talking about Kc or Kp. Okay, so that is, it's always the rate of forward reaction over the rate of the reverse reaction. Okay. Okay. So that's what she used here and got the value, this value. Yes, who else got a different answer, or we all got the same answers? Someone has this microphone on. Galaxy J2. Kindly mute your mic. Galaxy J2 doesn't have a name. Anyway, so let's continue. Yes, anyone with a different answer? Okay. Okay. That is Elizabeth. Okay. Yes. Let me call another person. Kwayebwa is the host. Let me call Elom. Gidisu Elom.
Sir.
What answer did you get?
Sir, I just entered the class.
Okay. No problem. Then we have But you are following, right?
Yes.
Okay, Michael Fosu. Michael, what answer did you get?
I'm still on it.
Wow. So let's proceed because there are a lot of questions we have to answer. It's a broad topic though. So as Lisa, is it Lisa? Yeah, as Lisa said, the equilibrium constant can be calculated by using rate of the forward reaction over the rate of the reverse. Okay, Seraphine has 0.02. That is excellent. Brilliant. Brilliant. You should be talking so that becomes interesting. Don't just type. We want to hear your voices. Okay, so let's move on. So this is the solution. So as you can see, Kc is K forward over K reverse. So when you go back to the question, it says that the forward reaction rate is 3 times 10 to the minus 4 per second, and then the reverse is 1.5 times 10 to the minus 2 per second. So we are just doing substitutions here. So Kc is equal to K forward over K reverse, giving us 3 times 10 to the minus 4 over 1.5 times 10 to the minus 2. So this becomes calculator where you just punch and get your answer, 0.02. Are we okay so far? Are we good to go?
Yes.
Very
Yes.
good. Excellent.
Yes.
Now, let's come to this question. Okay, Michael, 0.02. Good. Which quantities are equal in a dynamic equilibrium? So there are two parts to this question. The first part of the question has this as your options or your alternative answers. So you are going to select whether 1, 2, 3, or 4. Which quantities are equal in a dynamic equilibrium? That is when we have chemical equilibrium. Which of these statements are true? Do we say the moles of reactants always equals moles of products? Or the mass of reactants always equal mass of products? Or the rates of opposing reactions are equal? Or we cannot determine this without temperature information? Which of this is correct? This is just 3 seconds question we are discussing based on what the notes we've gone through. Yes, anybody?
Please, I think it's 3.
3, okay. That is excellent. But we are not accepting it yet. Let's call another person. Who else? Who is ready? Akoswe. Which option are you going for?
So please, I'm coming.
Say.
Yeah, Gidisu.
I'm going for the 4th one.
Okay, we cannot determine without. Hello, can you hear me? Yeah. The host, you muted me, right? Who is the host? Amankwaibua. But you don't want me to talk. Okay. Let's continue. Yes, we are still waiting for answers. We have 2 answers now. 3 and 4. Yes, Nanama, what are you going for?
I agree with the 3.
You agree with the 3. Good. 2 supporters for 3. 2 against 1. Okay, let's not waste the time. So the answer is number 3. The rates of opposing reactions are equal. I think we established that. When you go to the previous slides, it's just that they have changed the grammar here. What change it brought for me? You guys were the loss. You go there. You see. Therefore, at equilibrium, the rate of forward reaction is equal to the rate of reverse reaction. So this is what we learned. So you are supposed to apply this in this objective question. So the rates of opposing reactions are equal. Okay, so let's move to the second part of the question. If the rate constant for the forward reaction in equation 15.1, that is this, is larger than the rate constant for the reverse reaction, will the constant in equation 15.5 be greater than 1 or smaller than 1? Yes. There's also 5 seconds question. This is a 5 seconds question. Yes, anyone? Seraphim. Seraphim Ja. Tell us, what do you think? Will the rate constant, that is, will the constant in equation 15.5, that is equilibrium constant rather, be greater than 1 or smaller than 1?
Sir.
Yeah. Kidisu.
Smaller than 1.
Smaller than 1. Okay.
Smaller than 1.
Okay, why do you say smaller than 1? No reason. Should have a reason for your answer.
Sir, I have, but how to explain it is the problem for me.
Why? You can't speak English. You can speak Chi or something. Or you can speak English, but you don't know how to put it in words. Anyway, that is your idea. Let's call her a lady. Phoebe, what do you think? Phoebe. Phoebe. Just give this. Just it's either this or that. We just want your view. Oh, doesn't want to talk. Okay, let's call Salma. Salma. Greater than 1 or smaller than 1? Wow. Okay, so Lisa.
Yeah.
Will it be greater than 1 or smaller than 1?
Smaller than 1.
Okay, so today you all got it wrong. Let's read the question. It says that if the rate constant for the forward reaction is larger than the rate constant for the reverse reaction, we always know that the rate equation is even here. It's always the equilibrium constant equation is always K forward over K reverse. So if we are saying K forward is greater than K reverse, then definitely our answer should be greater than 1. For example, if here were 2 and here is 1, 2 over 1 is 2. If here were 0.4 and here is 0.2, that will give us 4 over 2, which will also give us 2. If here were 8 and here were 2, that will give us 4. Are you getting the concept? Yes. So this one is not even chemistry. You just apply mathematics. Yes. So once you remember this formula, you just test some values and see whether it will be greater than 1 or smaller than 1. And then you are quick to go. I hope you are okay with this.
Yes.
Very good. Okay, how do we know when equilibrium has been reached in a chemical reaction? These are all, we are just revising for the sake of those who are not here. Then we move to more serious. Yes? How do you know?
Please, the forward reaction will be equal to the reverse reaction.
The forward reaction will be equal to the reverse reaction. Excellent. Excellent. Who else? Okay, to add to that, we can also decipher or know when equilibrium has been reached in a chemical reaction if the concentrations of reactants and products no longer change. That is another way you can, aside the forward reaction being equal to the reverse reaction, the concentration of reactants and products should also not change. So when the concentrations of the reactants and products no longer change, we also conclude that equilibrium has been reached in a chemical reaction. Good. So based on the notes I gave last week and the revision we did this morning, let's write equilibrium expressions for Kc for the following reactions. So we have 2 moles of ozone being converted to 3 moles of oxygen. What will be the Kc? So let's take the A part. Who is done? You should all get involved. Try and...
Sir,
Yeah. Who is speaking?
Sir Michael.
Okay.
Kc is equal to
Mhm.
oxygen squared raised to the power 3
Oxygen squared raised to
divide
the power 3.
over
It should be square bracket
2
first, right?
moles of oxygen. 2 moles of oxygen.
Continue. Yeah.
2 moles of oxygen raised to the power 3 over 3 moles of oxygen raised to the power 2.
Okay, that's your idea. Not bad. Who else? That's good. I like people who contribute because it's very key in class. This one, you are not even seeing each other, so I don't see why we should be hiding. Let's come out, let's talk, and we'll be going back to school very soon. And you'll be surprised you'll be meeting some of these questions. If not, in your end of term, your WASI very soon. Yes, Nanama.
Is Kc is equal to
Mm-hmm.
square brackets O2 with square brackets O2 raised to the power 2 divided by square brackets O2 raised to the power 2.
Good. Let me write your answer down. That's good. Yeah. So that is from Nanama. Okay. Let's call another person. Perez. Yes, Perez. Perezi. Okay. Gideon Ajay. Okay. Kelvin.
Sir,
Yeah. What was your result?
A.
Yeah, for
That
A.
is equal to concentration of oxygen.
Mm-hmm.
Concentration of oxygen gas
Okay.
square
Okay.
over concentration of oxygen subscript 3 square.
Okay. So let's look at it together. Let's go back to the previous slides and then we'll get what we are doing here. So let's look at this equation. Look at how we did this one for KC. Here we even have two reactants and two products. So assuming it was only A going to maybe C, it will become the concentration. Is that why we use square brackets for the concentration of C raised to the power C. So the stoichiometric mole, that is the number in front of the product. In the balance equation, the number in front, that will be the power over then the reactant. You see the reactant here, A. And then the number of moles of A is also A. So raise the power A. So when we come here, come to this problem, here we'll have Kc being equal to the concentration of we are going forward, the forward reaction. So the concentration of O2, that is the product. But what is the number of moles there? 3. So it should be raised to the power 3. All over the concentration of ozone, that is O3. And then the number of moles is 2. So raised to the power 2. Are you okay with that? Okay. So Perez says I should solve the A so that we can solve the B and C. I think I've already solved the A. Is it clear for everyone? Perez, is it clear for you? Perez?
Yes.
It's clear, okay.
Yes.
So let's solve the B and C. So as we're saying with the let's do this. With the first one, KC should be equal to, then we'll have the concentration, so square bracket, of the product. What is at the right side there? We have oxygen gas. We have oxygen gas. Let's see, am I muted? No. So that will be O2. Then this is raised to the power. So we look at the number of moles here. The number of moles is 3. So raised to the power 3. Then over the reactant. So you have that one to be concentration of ozone. Concentration of ozone. That will be O3. O3. Then that is the number of moles here is 2. So raise to the power 2. Raise to the power 2. Yes, so this gives us the answer for the A. That's how we solve it. So let's look at the B. Who is done with the B?
Sir,
Yeah.
for the B.
Yeah.
So that is NOCl, concentration of NOCl square
Okay.
over NO square times Cl subscript 2.
Excellent. That's good. That's good. That's good. Then the third one.
The,
Yeah.
the concentration of AgNH3 2 plus, that's all raised to the power 1,
Okay.
over concentration of Ag plus, it's also raised to the power 1, and concentration of ammonia is raised to the power 2.
Excellent. Excellent. What's your name?
Perez.
Perez. Good. Good. So Perez is following now. Excellent. Good. So let's move to the next. Yeah, so these are answers here. So if you got these answers, then you are right. You're on track. So let's look at this few concepts too. Sometimes we use these concepts in section A especially. It can also be in section B, a sub-question. The equilibrium constant of a reaction in the reverse reaction is the reciprocal of the equilibrium constant of the forward reaction. I hope you all understand what reciprocal is. What's the meaning of reciprocal? Yes? Anyone to help us with?
Like opposite.
Opposite. Yes, who else? Mathematically, what is reciprocal? Reciprocal is opposite, right? That is grammar. But we want the mathematics meaning. Yeah.
The vice versa.
Vice versa. It's also English. Mathematics. How do you write reciprocal?
Sir, it will turn upside down.
To turn upside down. You are still giving us English. So, okay, let me give you an example. Okay, upside down. Let's say you have 2. What is the reciprocal of 2? What's the reciprocal?
1 over 2.
1 over 2, excellent. So that's what I'm looking for. So a reciprocal should be 1 over the value, right? So what we are saying here is that the equilibrium constant of a reaction in the reverse reaction is the reciprocal of the equilibrium constant of the forward reaction. So here I have N2O4 being converted to NO2. Let's assume the equilibrium constant for the forward reaction is written this way. So we have NO2 over that. We are getting 0.212 at 100 degrees Celsius. If we are being asked to find the equilibrium constant, okay, we are being asked to find the equilibrium constant for the reverse reaction, what will our answer be? What will our answer be? What will be our expression? That is when you are moving back from NO2 to N2O4. Yes, any ideas? Using what our friend told us, that is 1 over the value. Here we are looking at the constants, which have been calculated for us already as 0.212. So I'm interested in the value here. So if the equilibrium constant for the forward reaction is 0.212, what will be the equilibrium constant for the reverse reaction? What will be the value? Yes? Anyone?
Um, 4.717.
4.717. Brilliant. How did you do that? Who is this?
Salma.
Salma. Good, good. How did you do it?
That's 1 over 0.212.
Excellent. Okay, Ja Sarafin also gets 4.716. That is brilliant. I think we are all following. Excellent. So this is, yeah, so that will give us the expression there. So when you approximate, you get 4.72. Okay. Okay. Let's come to the equilibrium constant when the reaction has been multiplied by a number. So here we see the equilibrium constant should be raised to the power that is equal to that number. Okay. So excuse me. Yeah, so we have this reaction here. N2O4 is being converted to 2NO2. And then the equilibrium constant is still 0.212. Now, what will happen if I rather have, let's see, 2 moles of N2O4 going to 4 moles of NO2? What will be my equilibrium constant now? Using this expression here. Did you understand my question?
No.
Okay. You see, what we are trying to state here is that the equilibrium constant of a reaction that has been multiplied by a number is the equilibrium constant raised to a power that is equal to that number. So for example, with this reaction, assuming I multiply through the whole equation by a number, let's say if I multiply through the whole equation by 3, then here will become 3 moles of N2O4, then here will become 6 moles of NO2. So if I should ask you to calculate the equilibrium constant for the new reaction I've given you, that is the 3 moles of N2O4 going to the 6 moles of NO2. What do? You just raise this value here, you raise it to the power 3. Okay? Because you should have realized that I was multiplying through by what? 3. So if I'm giving you, let's say, the new reaction to be 2 moles of N2O4, and then here becomes 4 moles of NO2, what will be the equilibrium constant of the new reaction?
Sir,
Yeah, Lisa.
0.045.
Okay, so how did you do it?
I raised 0.21222. I
Okay,
squared it.
excellent. Because you realize that the new reaction has been multiplied by 2, right?
Yes, please.
Very good. So this is what we are talking about. So the rest of you, that's what Lisa did here. And we have to square this value to get the answer. Okay, so when you square this, you get Lisa's answer. Can we move on?
Yes.
Good. So we have a new problem here. How does the magnitude of the equilibrium constant Kp? This it works for what the concept we just looked at here. Manipulating the equilibrium constant. It works for both Kc and Kp. Okay. So here we have Kp here because we are dealing with gases. This hydrogen gas, iodine gas, this hydrogen iodide. It's also a gas. So how does the magnitude of the equilibrium constant Kp for the reaction 2 moles of HI being decomposed to A2 plus I2 change if the equilibrium is rewritten as 6 moles of HI going to 3 moles of H2 plus 3 moles of I2? How does it change? Or what will be the value of the new equilibrium constant? What will be the new Kp? The new Kp value. Yes.
Sir,
Yeah. Who is talking?
tell me,
Your name?
Perez.
Perez, okay.
Sir, will it be 0.212 to the power 2?
This one we've not been given the Kp value. We are not using the value here. So just we are not been given anything. We are not using this one. This one is Kc. This is a new question. So I just want the expression. So Kp.
Sir, the Kp will be raised to the power 3.
Excellent. So that's what I'm looking for. So the Kp will be raised to the power 3 because you are multiplying through the equation by 3, right?
Yes, sir.
Very good. So the new equilibrium constant is equal to Kp raised to the power 3, as our brother said. So this, what we do is some simple concepts. You might be asking objectives. Okay. So let's move on to another problem. We have a hypothetical reaction. Hypothetical means here is just an example. We don't have any reaction in the world like Y plus Z plus A. I going to A, but I'm just using this as an example. And then we have the equilibrium constant as 4.0 times 10 to the minus 2. Given this equilibrium constant, okay, what is the value of K equilibrium for the reaction 4 moles of A going to 2 moles of Y plus 2 moles of Z? Is it 25, 5.0, 0.016, or 6.3 times 10 to the power 2? Which are we going for? Study the question carefully because this is quite trickish. If you make some mistakes, the wrong answers are there.
Please, is 3.
3.
Option 3.
Option 3, 0.016. Who is talking?
Salma.
Salma, why do you choose option 3?
I raised 4.0 times 10 raised to the power negative 2 to
Why
2.
did you do that?
Because the first the forward reaction. In the reverse reaction, the second equation, was gotten by multiplying the moles of the first equation by 2.
By 2.
Yeah.
Brilliant. Good. But we're still waiting for more answers. This is not really correct. There is something missing. I like her reasoning. She has used good reasoning skills, but it's not that perfect. It's not the best. There's still more to be done. Yes, anyone else to challenge? I'm not accepting the third option, although it's a bit close to the answer. Anyone else? Yes, Amankwa Ibua.
Yeah.
Do you have a different answer?
I think it's the D.
The D. Why should it be D?
Hey, the 4, sorry, and the D.
The 4, yeah, the 4. Why should it be the fourth answer?
Yeah, because with the first equation, the reactants were the Y and the Z.
Okay.
And the product formed was the A. But looking at the second equation, although it has been multiplied by 2 throughout, there was a change, as in the A rather became the reactant, and the Y and the Z became the products.
Excellent.
So it means that before you raise the Kc value, the equilibrium constant value to the exponent 2, you have to divide it, as in it has to be 1 over that answer.
Wow.
Because the positions changed. That's what I think.
Good. The reaction has been reversed.
Yeah.
Okay. So when you do that, then you can now square it.
Yeah.
Okay.
That's what I think.
Good. That is a good reasoning. That is good. Yes, anyone else? Anyone else? Okay. So what Yebua was saying is true. There are two things that have been done here per our manipulation. We said that from the first okay, this is the first concept here, that the equilibrium constant of a reaction in the reverse reaction, that is when you reverse the reaction, as he was saying, the products rather become the reactants. We have to find the reciprocal. So we did this example where we had to find 1 out of 0.212 because we realized that we reversed the reaction. We wrote a different reaction altogether for this. So with that, if equilibrium constant is 1 out of the equilibrium constant for the first reaction, then we also know that when we multiply through an equation by a number, then we have to raise that the new equation's equilibrium constant by that number, as we're looking here. So with this equation, two things have been done at the same time. So our new K2 value, or our K2, if this is K1, if this is K1, then our K2 value should be 1 out of K1 squared. That is this. So the second equation is twice the first and also reversed. So the equilibrium constant of the second equation is related to the first this way. We can write K2 as 1 out of K1 squared. So it should be 1 over the first equilibrium constant squared, and we'll arrive at 630, which is the same as 6.3 times 10 to the power 2 in standard form. Are you okay with that? Are you okay with that?
Yes, sir.
Excellent, excellent. You guys are doing well. Everyone should talk. If you are not getting anything, this is the time you should talk. We realize that all we are learning is linked up. We looked at rates of reactions and we are applying that concept here. So if you don't get this, we move to another concept, you'll be in trouble. So you have to be following. Okay. So I think we looked at this question last week. So this is an application of that relation we had there. Synthesis of ammonia from nitrogen and hydrogen. We have this reaction. You have to calculate the Kp for the reaction at a temperature of 300 degrees Celsius. And here you have been given units for the rate constant. The molar gas constant. And we also have our Kc value as 9.60 without a unit. So what we do here is we first find a change in number of moles. So that will be products minus reactant. So that will be 2 minus 4. We got negative 2. Then the temperature should also be in Kelvin. The reason is that when you look at the molar gas constant, we have per Kelvin as part of the units. So we have to record the temperature in Kelvin. So we change the 300 degrees Celsius to Kelvin. Then we remember this reaction. Here should have been delta N, change in number of moles. This equation rather from our previous slides. So we just input the values there. This is our Kc value. We put this and then we work things out and we arrive at 4.33 times 10 to the minus 3. That's what we looked at last week. So I have here this one for us. Let's try this. With this equation, we don't have any unit for the molar gas constant. And we don't have any units given to for the Kc. So don't be worried about units. So your Kp value, I think I shouldn't have brought this. The answer is already there. Should have worked it out to get this. So when you get home, you can work the exercise 2 out and make sure you get the same answer. Are we okay?
Yes, please.
Only one person is okay. Or she's speaking for all of us. Okay. So this is for you. If you are okay, you should be able to solve this. The following concentrations were obtained for the formation of ammonia from nitrogen gas and hydrogen gas at equilibrium at 500 Kelvin. The concentration of nitrogen gas is 1.5 times 10 to the minus 2 mole per dm cube or molar. And then the concentration of hydrogen gas is 0.03 molar. And that for ammonia is 0.012 molar. You have to calculate the equilibrium constant Kc. Yeah, this concentration. So Kc. Let's do this quickly. Yes, who is done? Akwasu, are you done?
Yeah.
Yeah, Akwasu, are you done?
No.
Okay. What about Sarafin? Are you done? Okay. No. The rest says 26.67. The rest to me work it out again. Make sure you first have to write a balanced equation for the reaction. You have to write a balanced equation. Then you know the number of moles of products and reactants. Then you can raise the concentrations to those powers. Three 555.6. That is Amankwa Yeboah. 355.6. Okay, that is his answer. Let's keep waiting. The ladies in the house, let's get your answer. Okay, we have 355.56 from Nanama. Okay. Yes, anyone else? We are still waiting. Okay. I think I might have made a mistake here with the calculations. Let's go into it for the KC. Let's work it together. I hope you can still see.
Yes.
Okay. So KC should be equal to, before we do that, let's write a balanced chemical equation. What will be the equation? We have N2. Yes, the chemical equation, the balanced one. Who did that? Let we do this together. I think Lisa, right? Lisa also gave us an answer. So Lisa, give us the balanced chemical equation, then we can proceed.
Okay. N2, N subscript 2.
Okay.
Plus 3.
Okay, 3 moles of
H2.
Okay, hydrogen gas. Okay.
And the product is?
So we have this giving us, let's see. Okay, the products you have
2NH3 subscript 3.
2NH3. Okay, so these are balanced chemical equation. So the next step will be to write the Kc. So Kc should be equal to, okay, Kc should be equal to, you have the fraction sign there. So that will be the concentration of ammonia, that is the product, raised to the power 2. Is that okay for all of us?
Yes.
So we have 0.012. We are raising this to the power 2. Raising this to the power 2. Because there are 2 moles there. Then all this over. Then we have the concentration of the reactant. Okay, someone is. Okay, Perez also got 355.6. Okay, that's fine. The reactants, and is this 355.6 molar raised to the minus 2. Okay, Lisa is even giving us a unit. That's good. That's the best answer. Think here we should have a unit because the moles will not cancel out. This would be 4 and this would be 2. So yeah, good. So N2 concentration of nitrogen is 1.5. Sorry, 1.5 times 10 times 10 times 10 raised to the power negative 2. So this is multiplying. The concentration of hydrogen should be raised to the power 3 because it has 3 moles. So we have 0.03 exponent 3 exponent 3 exponent 3. Oh, sorry. Exponent 3. So we punch in these values. Think, let's do this together. So 1.5 times 10 to the minus 2. I'm solving the denominator first. Times 0.03 all cubed will give me 4.05 times 10 to the minus 7. So I'm going to divide 0.012 all squared by the answer. So that gives me 355.56. Good. So our KC will be 355.56. Here we should get a unit. Because this is squared, we'll have molar squared. Molar squared. So let's say molar squared. You don't write this, but for the sake of our lesson, I'm trying to show you how it will cancel out. Then here we have 1 molar here, and then we have 3 molars there. So giving us 4 molars. So molar. So when you do the cancellations, you'll be left with molar raised to the power -2. I think that's what Lisa gave us. Yes, that is good. Yes, so any questions so far? We are not done with the topic though. Our time is up. So our unit here should be molar raised to the power -2. Extra time. Wow. So in case I do extra time, what will be in for me? Because you are going to buy my time. They will pray for me. That's fine. I like prayers. Prayers is good. But you know, you are not the only ones I teach. Yes. I get you. There is a lot to cover. There's a lot to cover. You guys are doing well. There's a lot to cover. But we'll have to end here and then continue another time. But I'm still asking if there is no question.